All right, everyone, we just got it okay to start the final planetarium show of the day. So I'm going to put away our space trivia questions because now we're heading into the unknown. Ooh. And good afternoon, everybody. Welcome to the Morrison Planetarium. Really quickly, I just want to introduce myself. My name is Goose. I'm going to be your planetarium presenter, and I'm actually a person. I'm standing right behind you at the top of the planetarium. Hey, good afternoon. Good to see you. Don't hurt your necks, though. Look forward into the dome before you because everything that you see in purple is going to be one really big screen. Thanks to the help of 6 different projectors hidden throughout our dome. And folks, I'm really happy to have you here today because you're doing my favorite planetarium show. This one's different from all the other ones that we've done here today. This one's called Tour of the Universe. Now, in Tour of the Universe, you're going to be hearing my voice for the next 30 minutes. And we're going to be starting off pretty close to the Earth as I free fly you through space to the very edge of the observable universe, what we humans can see. But before we do that, I got to go over some quick house rules just so that we're all on the same page and have a good time. First off, there's no food or drinks allowed in, so if you brought any snacks, make sure those are put away till the end. We want to keep this place nice and clean for all the, just keep it clean in general. Also, if you have any cell phones, smartwatches, anything that makes bright white light, now is a great time to put away those devices. These can be very distracting and takes away from the show. And if you need to leave early for any reason, the exits are going to be at the top of the planetarium, so always make your way up the stairs to exit. And if climbing the stairs poses a challenge for anybody, do not worry, just remain seated. We'll have a staff member escort you to a lower exit when the show's over, so just stay seated for a bit longer. And last but not least, this show can be quite immersive thanks to our 75-foot dome above us. If at any point during the show you start to feel overwhelmed, you experience motion sensitivity, there's a really quick and easy trick to ground yourself. All you have to do is close your eyes, take a few big deep breaths, then your brain will remember that you're sitting in a planetarium in San Francisco and not hurtling towards the edge of the observable universe, at least not more than the usual. Hee hee hee. But with that being said, it looks like we're ready to go. So I invite you to sit back, relax, gaze into the dome before you, because here comes Tour of the Universe. All right, everybody. As I mentioned, we're going to be starting off pretty close to the Earth, but not right on it. We're just flying above. You can see all the city lights down below. We're currently starting off our tour of the universe here at this amazing, incredible human feat, the largest thing we humans have ever put out into orbit around in space. What we're looking at, folks, is called the International Space Station, or the ISS. And just to let you know, the International Space Station is a research facility. It's a laboratory that orbits around our planet Earth. They conduct many different types of experiments up here, and there's quite a few things that have been invented up here as well. For example, if anybody's wearing Velcro or uses Velcro, it was invented on the International Space Station. And most folks have probably used a ballpoint pen, maybe in your office or in your day-to-day life. That was also invented up here as well. So lots of great things were invented here on the International Space Station. But what's also really amazing is, again, it's the largest thing we humans have ever put into orbit around our planet. But how large is it? Well, folks, it's roughly about the size of an American football field. If you've never been to an American football game, that's okay. You can also use the entire museum that we're sitting in right now. That's about how large it is. But what's really incredible is how fast the International Space Station is traveling. It's traveling at a whopping 17,000 miles per hour, where it orbits once around the Earth every 90 minutes, and it experiences 16 sunrises and 16 sunsets a day. Whew, how romantic. And also, this looks really far away from our planet as well, but it's not too far either. It's only about 250 miles above the surface of Earth. 250 miles for us Californians, that's like going from San Francisco to Santa Barbara. A nice little road trip to get away with the family for the weekend. So not too bad. That is if you were able to drive directly vertically up. But to tell you the truth, folks, this is as far as we put humans out into space nowadays, only 250 miles above the surface of Earth. The reason why is because traveling into space is quite costly. You got to get yourself a rocket ship. You got to leave Earth. You need so much rocket fuel. Then once you're out here in space, you got to account for all the food, water, all the air you're going to be breathing, so it gets quite costly quite rapidly. But the International Space Station is just the first stop in our tour of the universe, so now we're going to see it start to slowly fade away to the city lights down below. And if anybody can make a guess of where we are on Earth, where we're flying above, go ahead and place your bets right now. And also, before we lose track of the International Space Station, I want to add a nice little orbital path so we can see it as it starts to slowly fade away. And hey, look at that. It looks like we're flying just above Italy. So if you said Europe or above Italy, you got it correct. And folks, we're now so far away, we're able to see our entire planet Earth from this vantage point. And I want to let you know that the space program that we're using here right now for the show is something that you can go home and download if you want to fly through space just like how we're doing. The space program that we're using is called OpenSpace. The URL is openspaceproject.com. You can come across the link, download it, and it's a whole lot of fun. They're still working on OpenSpace, so it's not finished. So they're constantly updating it all the time. And also, OpenSpace uses real-time information. It pulls images from satellites that took photos from yesterday. So all the clouds that you're going to see in a moment, that's what the clouds look like yesterday around noon. But also, since it pulls from real-time satellites, it uses a whole lot of processing power. And if you're a person that doesn't have a amazing computer or storage, that's okay. We also have another great alternative for space programs. If you want to search up NASA's eyes, don't have to download anything, and you can fly through space, and it's a whole lot of fun. But in here, we're using OpenSpace. But now that we know what we're using, let's make our way over to our nearest natural neighbor to us in space, the moon. And folks, we humans have been to the moon before. That was between 1969 and 1972, thanks to NASA's 6 Apollo space missions that brought a total of 12 incredibly lucky guys to walk on the surface of the moon. They got to conduct science, and of course, they had some fun up here as well. They got to play some golf. But again, last time we sent humans to the moon was 1972, a little more than 50 years ago or so. But don't worry, folks, we humans are making a return trip back to the moon in the next few years, thanks to NASA's new space mission in the works called Artemis. Pretty much with Artemis, NASA wants to send humans to Mars. But before we send humans deep into the solar system, we need to figure out exactly how we're going to be able to live out here in space. So the moon is the perfect stepping stone to figuring out the logistics of that. What's really incredible is that they're going to be sending the first woman to the moon, but not only that, they're also going to be sending the first person of color to the moon, but not only that, they're also going to be setting up lunar bases throughout our moon. Pretty much our technology has greatly improved in the last 50 years, so we're able to conduct much more science in a much more compactable size. And one place that we definitely want to set up a lunar base is the south pole of the moon. The reason why is because we found ice there, and that's going to be very helpful because we can melt that ice. We can pass electricity through it. We could separate the hydrogen and oxygen, and both that stuff's really valuable when you're far away from home. So look out for any news about Artemis in the coming years. We humans should be heading back to the moon relatively soon. And folks, when you look over the moon here from Earth, sometimes the moon feels incredibly close. It feels like you can reach out your arms and touch it. But the moon's really, really far away. It's about 240,000 miles away from planet Earth. Whew, that's far. Now, some of the adults in this room may have a car with that many miles on it, and if you take better care of your car than I do, you can even imagine driving to the moon if you drove nonstop for about 4 months, going about 80 miles per hour. Although I wouldn't recommend it, the roads out here are poorly maintained. Hee hee hee. And from here on out, folks, we're going to need to use a more useful measuring stick because at this scale, using miles is kind of like using inches to describe the distances between cities because space is so big. So astronomers use a more convenient measurement known as light speed. And light travels at a mind-boggling speed of 187,000 miles per second. That's about 300,000 kilometers per second. So while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so since, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like a short pause in conversation. But at last, folks, it's time for us to leave the moon behind. So everybody say, bye-bye, moon. Oh, so cute. And now, folks, we're going to see the moon start to slowly fade away, just like how we saw earlier with the International Space Station. And just like before, I want to add some trails so we can keep track of stuff out here in space, because space is quite large. Now, all these blue lines that we're seeing, except for the one in circle right now, that's the moon's orbit, all these other blue lines are the trails of the planets in our solar system. And on our journey today, we're going to be traveling much faster than the speed of light. We're going to be traveling at the speed of the human imagination, thanks to the help of computer models like OpenSpace, showing us the most accurate images and information available to us. And now the nearest star to us, the sun, should be coming into view. So here comes the sun. Do. And folks, the sun's also incredibly far away from Earth as well. The sun's about 93 million miles away from our planet. Whew, 93 million miles, that's a good distance away. But for the fastest thing in the universe, light, to travel that 93 million miles, it still takes light about 8.5 minutes at the speed of light. And this is a great concept to keep in mind, because even though light is the fastest thing in the universe, it still takes time for it to travel these great distances. And again, great concept to keep in mind, because let's say we're looking at a star that's 70 light years away. We're looking at that star as it looked like 70 years ago, because the light that we're just seeing right now took 70 years to get to us. So when you look at really far away objects in space, it's like looking back in time in a sense, which is amazing. But now that we have a nice bird's eye view of our solar system, let's do a quick refresher of what we have, shall we? Right in the middle, we have our star, the sun, the biggest thing by far. The closest planet to the sun, we have Mercury. Then we have Venus, Earth, that's us, and then Mars. These are the rocky terrestrial planets. These are places where we can actually land a spacecraft on. And then past the orbit of Mars, we have the main asteroid belt. And this is where you can find a lot of space rocks. Just be careful driving your spaceship through here. And then once we pass the main asteroid belt, we have the really big planets. We have the Jovians. We have Jupiter, the largest of them all. Saturn, famous for its rings. Then we have the icy Jovians. We have Uranus, the funny one, and Neptune. And of course, we can add everyone's favorite and lovable dwarf planet, Pluto. So here comes the orbit of Pluto on screen. And Pluto's orbit's on the very top of our dome right over here. And what's really amazing is that a lot of people don't realize that Pluto hangs out here in this outer part of our solar system called the Kuiper Belt. And I know a few of you in here are probably wondering to yourself, what's the Kuiper Belt? I've never heard of that before. Well, folks, this is the Kuiper Belt. So what you're mostly seeing are icy asteroids, short period comets that don't travel too far away from the sun. And this is all past the orbit of Neptune. And what's really amazing is that in the year 2006, our technology greatly improved. Our telescopes were able to see really small objects farther away. And we came across more than 400 objects out here in the Kuiper Belt region. And some of that stuff was bigger than Pluto. So we couldn't call all these things planets. There's just way too many of them. So all the astronomers on Earth had a great big meeting. They had to figure out what exactly you need to be considered a planet. And they came up with 3 different criteria. And folks, that was the day in 2006 that Pluto went from being a planet to a dwarf planet. And I know a lot of folks still have hard feelings about it. I still kind of do. But that's the really cool thing about science. Because as our technology improves, we're able to make better improvements and adjustments. So science is constantly updating. And I just love that about it. But I'm going to put away the Kuiper Belt region because that's just a whole lot to look at, to be honest. And now on screen, folks, I'm going to be adding the many different spacecrafts we sent out in the 1970s to explore our solar system. Now on screen, we have the trajectories of Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2, and the latest of them all, New Horizons, which flew by Pluto in 2015. We could see that interaction just by Pluto's trail. All of these spacecrafts are all traveling fast enough to escape the sun's gravity and leave our solar system behind. But even the most distant of these robot adventures, Voyager 1, has not traveled as far as light travels in a single day. In order for sunlight to travel all the way out to the orbit of Pluto, it takes sunlight about 5 hours at the speed of light. 5 hours to get all the way out there. Not too bad. But, folks, it's time for us to leave our planetary scale behind us because now we're going to be heading out into interstellar space, the space between the stars. Distance now becomes so immense, it's going to take us about 4 years at the speed of light just to reach the next star system to us, the Alpha Centauri system. And it looks like Alpha Centauri is just right above us. So our solar system's right in the center. We're spinning around it. And just above, we have a star that's moving pretty close. That's the nearest star to us. And again, 4 years at the speed of light just to reach the next star system to us. But folks, that doesn't really put into perspective of how long it would take us to travel that distance. Well, if you're getting a rocket ship today, made your way over to Alpha Centauri, it's going to take you roughly about 8,500 years. Whew, and that's just a one-way trip. I hope you take some snacks. But folks, we're going to stop consider whether humanity has made its presence known beyond the solar system, because now we're stepping inside something called the radiosphere. And again, folks, we're now inside something called the radiosphere. This represents the current limits of the most distant radio signals humanity has ever broadcasted out into outer space, and it extends about 90 light years in all directions, emitting out from the Earth. This first began in the early 1930s with strong radio waves, early television, radar signal, and then later, the detonation of atomic weapons. All this stuff is emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. And humans were broadcasting well before the early 1930s. But the earliest radio was not quite powerful enough to escape the Earth. Since all these signals are electromagnetic, they're traveling at the speed of light. So this is kind of like humanity's electromagnetic footprint in the universe. And of course, the radiosphere is constantly expanding at the rate of 1 light year per year. So is anybody out there listening? And now, folks, I'm going to be adding these many markers to the screen. These markers indicate the many thousands of stars astronomers have discovered over the last 30 years, which has at least one or more planets orbiting around them. We call these planets exoplanets, and we're looking for any of them that are Earth-like with conditions suitable for life as we know it. So far today, we found more than 5,000 confirmed exoplanets in our nearby vicinity, 5,000 other worlds besides our own. And that number is going to be increasing as the years continue because we have space telescopes where their whole purpose is to find as many exoplanets as possible. In fact, if you look in the screen right in front of us above, you can see we looked in this one section of the night sky. We pointed a telescope for about 10 years there, and we found a whole heap of exoplanets. So as we continue to scan more and more, that 5,000 number will be increasing. Now, to say if any of them are Earth-like with conditions suitable for life as we know it, well, we cannot answer that question quite yet. Pretty much new space telescopes are being worked on. They're on the drawing boards, they got to get built and then launched into space. So we have a little while before we can answer that question. But the more important point here is that quite a few of these planetary systems are within that 90 light year limit of our radiosphere, and they could have potentially received our signals. However, since radio waves travel at the speed of light, if there is anybody that's out there able to listen in and answer back, the communication delays between hellos could be decades in time. And of course, planetary systems beyond the radiosphere, more than 90 light years away, have not heard from us yet, but eventually they will, as the radiosphere is always growing, but it becomes weaker as it does. But for now, folks, I'm going to be putting away those exoplanet markers away. But I'm going to leave our radiosphere up on screen. As huge as humanity's electromagnetic footprint is, it is nothing compared to our Milky Way galaxy, so keep your eyes on it. All right, folks, we're now looking down at our Milky Way galaxy. This is the galaxy we live in, and I have to ask, can anybody see their house from here? Just kidding. And folks, our Milky Way galaxy is incredibly large. If you wanted to cross it from one side to the other, it's going to take you roughly about 130,000 years at the speed of light. It's enormous. And the Milky Way is so huge, we estimate that there's at least 300 billion stars in the galaxy. If our recent discovery of so many exoplanets just within our small neighborhood within this massive star city is any indication, there could be billions of planets and potentially millions of Earth-like planets throughout the single galaxy. And before we leave the Milky Way galaxy, I want to show you what it looks like from the side. We live in a big flat spiral disk. It kind of looks like a big pancake or a frisbee from the side. It's very flat, at least our galaxy. And this is important because when astronomers want to learn about the universe, it's much easier for them to point their telescopes galactically north and galactically south, instead of looking at the flat part, the plane of the Milky Way, which has planets, stars, galaxies, nebulas, things that block their view of the universe. So keep that in mind. We like to point our telescopes galactically north and south. That's going to come important in just a little bit. But folks, the Milky Way galaxy is only one of many hundreds of billions of galaxies that comprise the known universe. So in this giant leap, every single point of light that you're now going to see no longer represents a star, but rather the location of an individual galaxy. Each galaxy containing hundreds of billions, perhaps trillions of stars. And we live in a local galaxy group, which contains about 30 galaxies large and small. Also includes the nearest large spiral to us, the Andromeda Galaxy. Only 2 million light years away, just next door, and heading right for us. We're going to get to know pretty intimately in about 5 billion years, so mark your calendars. And once the Milky Way and Andromeda collide and merge into each other, we will formally be known as Milkdromeda. Yeah, astronomers are great at naming things. And folks, as we continue zooming out, you're now going to realize that galaxies are not evenly distributed throughout space where they're in a nice little neat line. Instead, galaxies like to group together in large groups and clusters, or they like to create voids where there's very few galaxies or no galaxies at all. So we could see some galaxy clustering towards the center of our screen. We could see some voids off to the left-hand side of our planetarium dome, or on the right side. And this picture that we're now looking at represents the closest 30,000 galaxies to us in a space over 300 million light years across. We got to give thanks to an amazing researcher by the name of Dr. Brantoli, who compiled this amazing representation with the help of other astronomers working beside him over decades of time. So big shout out to Dr. Brantoli. I love flying through this galactic map. But now, folks, we have automated systems that are mapping even the most distant galaxies. So now we're about to see the large-scale structure of the universe. And remember, every single point of light that you're seeing, that's not a star, that's an individual galaxy. And by the way, the large-scale structure of the universe is not in the shape of a bow tie or a butterfly. Remember when I mentioned that we live in a big flat spiral disk of the Milky Way galaxy? Well, if you line up the Milky Way, it would line vertically, down just like so, up and down. And again, astronomers like to point their telescopes galactically north and galactically south because of the plane of the galaxy. It blocks a lot of stuff. But we still wanted to make sure that there was galaxies through the plane of the Milky Way. So we have this purple survey right in the center. You're able to see that we're still able to find galaxies, just not as many and not as far. Pretty much we have to wait for technology to improve, and once that happens, we'll be able to map out all the areas that haven't been filmed in yet. So it's just a matter of time. Oof, and speaking of time, we're almost out of it. So let's continue pressing on. Because now, folks, we're going to be encountering these really distant, faraway objects known as the quasars. And the quasars are going to be represented by orange dots on either side of the large scale structure of the universe. There they are. And the quasars are short for quasi-stellar radio sources. These blazing objects are all billions of light years away. So now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenage version of the universe. And before there was a teenager, there was a baby. So let's press back to a time before quasars, planets, stars, and even galaxies began to form. Folks, we're about to see the very edge of the observable universe. And here we are, folks, at the very edge of the observable universe. What we're looking at is something called the cosmic microwave background image, or the CMB image for short. All evidence indicates that the universe that we live in is about 13.8 billion years old. This is data compiled by Planck and other radio telescopes. And this is a very baby version of the universe, only 380,000 years after the Big Bang occurred, where space and time began. And this isn't your typical photo either. Instead, this is a temperature density image. You can kind of think of it like a filter for your phone. What we're looking at, or what it's showing us, are the light echoes of the Big Bang, which are color-coded, with the light areas corresponding to the hottest, least dense regions, and the dark areas, the coolest, densest regions. But these differences in temperature and density are extremely tiny. They vary no more than 1 part per 100,000, so really minute differences. But those tiny differences eventually gave rise to that large-scale structure of the universe that we saw moments ago, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. Folks, though our view here is of the outer edge of the known universe, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But folks, we've traveled as far back as the law of physics can physically allow us to go, so we only have one direction left to go. Back home, towards planet Earth. So let's find a nice entry point through all these quasars and galaxies. This looks like a great spot. And let's make a return trip back to planet Earth, everyone. All right, everyone, we're crossing an expanse of over 13 billion light years. We present you with this view of our universe and the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. We live in a golden age of astronomy with new generations of space telescopes extending the reaches of our eyes. And with that thought, I want to remind you all that astronomy is for everyone. You don't need to be a rocket scientist to enjoy the beauties and wonders of our universe. All you need is the night sky, and if you can, get away from the lights of our cities and look up. Even a good pair of binoculars makes for a decent first telescope. And there's astronomy clubs all around the world that invite people just like you to look through their telescopes and peer into the great beyond, allowing you to partake in the wonders that our universe has to offer. Now, astronomy as a hobby can offer an endless supply of satisfaction, and I do hope you'll join us, those who dream amongst the stars. But it looks like we just flew back into our Milky Way Galaxy, folks. We're heading straight for that radiosphere. And now we're flying back to our star system, our little neighborhood in the vastness of space and time. And now we're about to pass those spacecrafts we sent out in the 1970s to explore our solar system, passing the orbit of Pluto and the Kuiper Belt region. And now we're making our way back to the third rock from the sun, our homeworld, planet Earth. All the people that we know, love, ever learned about in history, all lived on this one planet. And now, folks, we're about to pass the orbit of the moon, the furthest we've ever sent humans out into outer space. And as we make our final approach back to planet Earth, this is going to be the end of our Tour of the Universe show. And I want to thank y'all so much for stopping by and watching with us today. I hope you did enjoy it. But hey, look at that. We're back home safe and sound, just in time for dinner time. And that's all the time that we have for today. So thanks for stopping by, and I hope you get home safely.